We'll start the class. So before we waited and hello everyone. Uh, Happy Independence Day, and I'm sorry for having a class today.
Evening, ma'am. That's fine, ma'am. Thank you. Thanks for accommodating even today also.
I hope it was not a trouble.
Not at all, ma'am. Thank you.
We'll get started with the class. And last time I said that few inquiries were there regarding that. I'll first discuss you guys wanted reference, right? So sir actually told that whatever the material which is being transcript, whichever is there, we were discussing that. Okay. I'm sorry. Is my voice audible properly?
Yes, you're audible.
Okay. Sir was those which transcript we were discussing that was there in other languages. Those things were not booked. Those were again material only. Those were just the transcript subtitles for sir's course. And then sir actually asked to take the buy the books, and yeah, if it is required, like um whichever was his transcript, that was only will be given. It seems Ramesh sir, I texted, this is what they replied. That's what sir told. Like you guys have to follow the class, and for reference, you guys have to whatever is given in the transcript, that subtitles for the sir's notes, it's already given. It will be under the NPTEL exam. So you that is the thing that you have to follow. Did you guys understand which one I was going to tell?
Madam, what is notes? Any notes is uploaded?
Sir has given the notes along with that. In that only the transcript is there, whichever for sir's class only they have written there. So that is all. Sir will actually not give notes or slides. It seems that is not the way sir do the teaching. Does the teaching. So whatever it's given in the NP that much only. And under the book section, we were trying to find that there were different languages, but English was not there, right? But actually, English is there in
Yeah, it is
yeah.
the text transcripts. Under text
Yes, it is a text transcript only. So from there only we have to study actually.
and I think you can download when you click the download for English. It goes
Huh?
to a Google. When we click download the
Hmm?
English text transcript, it goes to a Google Drive location, and search PPT slides are everything. It is there in the Google Drive. I mean, in PDF format.
Huh. But that is a screenshot of sir's
Yes.
notes. That is actually not the PPT, to be frank. Sir will not actually share PPT. That is not the way sir does the teaching. That's what I got from the students. And then sir will not be actually giving the notes also. If possible, we have to buy book exams. So that's what I got. And the regarding it will be MCQs only regarding the exam, and sir also will see if possible he will also be present for one or two classes in future. Sir will he will clear all the doubts when it's near the exams. That will be there. And anything else we thought we will discuss fatigue, so we will start up with fatigue unless until you guys have any other questions.
Yeah, you can start now.
It's fine, right?
Yes.
So today also we'll be discussing the previous assignments only, and then
Now third assignment is in progress.
Yes, if third assignment is in progress,
The
we
previous
will be.
third assignment similar to that particular chapters you can please discuss.
Yeah, I'll be discussing the chapter wise, or like whenever the question comes, whenever there is a doubt also in the concept, you guys can ask. We'll be discussing accordingly. And first, I thought today I'll show few microstructures. So this is a week 3 engineering fracture mechanics course, and Rashi again for those who are not there last class. And then this course is taken by Professor Ramesh sir, who is a chairperson at the Department of Applied Mechanics in IIT Madras. And we'll start with our class third course. Like last time I said that I'll be discussing the fatigue crack growth mechanism. Like few of you had a doubt regarding that, how the crack propagation will happen and everything. So first we will discuss this a bit, and then we will go to, I'll show you the few microstructure, how it is done. So like in crack, when there is, as we know, when there is a loading will happening, some amount of load plus and minus we can consider, and delta p, the similarly the same it will be happening because it is a cyclic loading, whether it can when it is in, it can be in tension compression, as well as like it can just be in tension only. The loads can keep oscillating. So when this is happening, the four and we are considering that there is already a crack present in the beginning, and this crack initiation starts happening considering the crack is very small. Like this is we are considering the surface crack as well. So the crack length will be A initially. And then crack initiation will be happening. There are four steps where the crack growth and then finally the failure will happen. In between that four steps, the first is crack initiation will happen, and can when crack initiation happens, considering that there are no cracks like surface, there was no cracks present, like perfectly sample, like there are no surface cracks or anything is present, but when smooth surface, it's polished surface, then when we are still applying the load, what happens at surface, it starts forming the cracks in all the possible direction, like on the surface. And some can even go deeper, like how now we will be seeing how the what are the stages of the crack can how it can form. And then once it forms, and we'll concentrate only on one crack, and we'll consider it has some amount of length A, and this is called, first stage is called crack initiation. And these crack initiation, like it will be only, we are considering it's a perfect solid where there are no defects at all in present inside, and then it is completely homogeneous. And these cracks, whatever it will be formed on the surface, we can remove these cracks by doing some heat treatment, by just doing the heat treatment like annealing or something. Annealing, we can remove all the cracks that are present on the surface that are formed due to the fatigue. And we'll also consider the delta P's applied variation in fatigue load is very low, and we will try to find out. And next, once the cracks is formed, second step is where crack growth will happen, and crack growth will happen in two different stages. Stage one, this is called second step, and stage two. And as we know, the load will be keep on varying. So it has, we will be considering it has some tip radius also. In stage one, what will happen? Crack growth starts deepening. Now it will be on the surface, and then it starts deepening. The crack will be deepening, and then especially it will be moving in the direction where there is high shear stress is possible. So like when there is no load, consider there were the image was like this, and then when we, this is after forming some amount of cracks, it is deepening, and now we will be still seeing in the step manner. And then now we will see that load is applied, it keeps on applying, and then it keeps forming, and then it will be growing in the direction where higher shear stress is present. And as we have seen previously, the higher shear stress will be at 45 degrees, and then so it will start along forming small it gets deepening in those direction. Here we are considering the load is up, tensile or in axial mode. And further, with increasing the load, what happens in second stage? The crack growth will happen in a planes where high tensile strength. Here, where high shear strength is present, the high shear stress is present in the stage 1, and later in the stage 2, where high tensile stresses are present. And then that's why we further where the maximum load is applied when as we know in fatigue, it will be something like this. So when the maximum load gets applied, and we are considering it is in tensile, and this is in compression. So when maximum tensile stress is applied, like then it grows in the direction where high tensile stress is present. That is in stage 2, and then further like involves crack movement in the normal direction. So further, when we remove the load and when the unloading will be happening, it gets reduced and it will be closed. But here, as we have seen, when completely no load is present, as you can see here, initially it was having 1, 2, 3, 4 striations. Once the one cycle was completed, here now we have the striations 1, 2, 3, 4, 5 striations, and then we have further, and then it keeps on repeating. And this once it reaches the length, like enough length in such a way that where it can act like a brittle material, once it reaches enough length, then failure happens, final failure. So these are the steps where the crack initiation, it will be happening usually at the surface, and considering the surface because it has higher energy, considering the material is homogeneous, and then crack growth happens in 2 different stages, where first is high shear stresses will be present, and in second stage where high shear stress tensile strength will be present. And once it keeps on repeating in the in fatigue mode, and once it reaches enough crack length, it fails in a final brittle manner. So I want to show you 2 images for that respective. So this is how the where the crack origin will be present, and then further where crack origin will be present, and then this it will be further having smaller striations inside the sample because of varying load. And then beach marks, that beach marks will be seen macroscopically, and once it reaches enough crack length, it will be failing in a brittle manner, and this brittle manner will be having granular structure, and it will be having shiny surface or something like that. And I wanted to show you a few images. And when normal tensile strength is happening, only we will be able to see slips will be occurring in one direction. But when the cyclic load will be applied, it will be having both intrusions and extrusions like this. And further, this is how the surface will be. The origin of the crack is at the where there is a edges, or there is a place where we can see that here it's easy to start crack, and then it will be propagating because the stresses also, we can say that because of this is a edge, stresses also will be high, and then beach marks also be observed, and final rupture has happened. And this is how the striations will be present. Like when you see in a electron microscope, you'll be able to see small striations. These are mainly because of what applied cyclic loading. So this is about fatigue crack growth mechanism. I hope now it is clear. And I think so Suresh had a doubt regarding this.
Yes.
Yes.
second week assignment, there was a question to arrange the steps in a sequence.
Yes, I remember.
That,
Was
that
the
direct to that question, just can you please discuss? Actually, there was
I forgot the question actually. Like
yeah, there was some arranging the steps in sequence,
so it
indicating
was
that.
these were the steps.
Pardon?
These were the steps. I mean to
No,
say.
it was given little different.
Okay. Can I just see the question and then I'll. Can someone read out the question? Do you have the question?
Yes.
Yeah, it's about the sequence of crack initiation.
Can
So
you tell me the options we
yeah,
have?
so the first, no, I can tell you the correct answer because it was there in sir's video.
Notes.
Anyway,
Yes.
yes, notes. So it is the first sequence. The start will be plastic deformation at the crack tip occurs because of high stress concentration, even at very low loads. Then plastic deformation is the slip of atomic planes due to shear stress. No, 1 minute. I think I'm. Correct. So second is plastic deformation in the slip of atomic planes due to shear stress. Then plastic deformation blunts the crack tip when unloaded. Then crack tip becomes sharp due to. I'm sorry. Third one was plastic deformation blunts the crack tip due to loading. Then finally, fourth one is crack tip becomes sharp due to unloading.
Yes.
These are the steps. Actually, in fact, the answer for the assignment is also given the same thing. But
Yes. Here we can see that. Consider that this is a sharp tip. This one here, how it was present, and we are applying a load. And as I said, the plastic deformation, as this is a material with sir has taken not a brittle material. It is it has some amount of ductility. So when we are applying a load, some amount of plastic deformation will be happening around this region. That's the reason why I have drawn in. Hello. Okay, I was able to listen my own voice. So first, because of the applied load at the crack tip, what happens? The plastic deformation happens at the crack tip, and then when we further apply the load, then the propagation will happen. As I said, first stage is where the high shear stress is present. It keeps propagating in that region, so it will be at 45 degree where the high shear stresses will be present. So it will be propagating in this region when as you know. So as I have marked it here, and then the atom movements slips will be happening in atoms where the high shear stress is present. And further, when we increase the load where it reaches a maximum load, and it gets blunt because it will be it will be going in a high tensile strength mode. So it will be now the crack will be going in this direction where the second stage will be present, and then crack movement will be happening in this way, and then it gets blunt because of the plastic deformation happening near the crack tip region. And once it reaches maximum and reduces the load, and it gets closed. Once it gets closed, the further there will be one more step striation that will be formed, and then normally and it go back to the sharp region how it was present here, or like how it was present here. But then there will be one extra striation that happened here, and but then at the end it will be either sharp or it will be having some amount of you can say it as sharp only because it will be easier for you guys. This is it. So the steps are still valid, right? Hello?
Yes, madam.
And then this final failure will happen only when once we reaches enough crack length, and then the final brittle failure in the form of brittle failure will be happening. But then here it is where like when you see in this region only, again when the unloading will happen, when it will be going to zero, no load, and then the crack gets reduced when it gets closed, and then the tip becomes very sharp. So the steps
Actually,
which I said.
the step 2, plastic deformation occurs at the tip of the crack due to loading. That is okay. That is clear. That is the first step.
That is the first step.
The second step, actually the assignment answer says it is slip of atomic planes due to shear stress. But I was thinking it is the crack advances impacted and blends due to plastic deformation.
Okay, what were you telling? Like first is plastic deformation will happen, and second is which step you're telling?
Crack advances and blends.
Why? Where will the shear stress will come then? Crack advances and then blunts. So see here we have to we have to go in a fashion. Now we will see like load, like stress, amplitude, and you have to tell me when this is a position and we have normal just crack now, and we're increasing the load, and we have not reached the maximum load yet. Sorry. So this is the maximum load that we have. And when we are increasing the load, first, initially, it will be having some amount of plastic deformation somewhere here. And then when overcoming that plastic deformation, we are still applying the load, and then the slip starts getting activated. The atom movement should be there, but then it cannot move in this direction because a tensile strength is not that enough that it will move in forward direction. Even in the third week lecture also, sir has discussed again regarding the fatigue mechanism, like how the crack growth finally at final stage, as we know, the shear stress will be maximum when at 45 degrees. The crack should be growing in this direction, but still it will be, when you see at the end, the propagation end result will be in this direction, not in 45 degrees direction, right? So that is mainly because at the maximum load, what will happen? The the crack will propagate where the high tensile stresses will be acting. So that's the reason why crack blunting will happen. At the same time, the plastic deformation, because of the presence of plastic deformation, crack blunt will happen. That will be in the third step. So before that, there is one more step where the cracks will be growing in the direction where shear stresses are high. So in between, first the plastic deformation will happen here. And here the shear will be activated, and once it reaches maximum, the crack will be propagating in the direction where the high tensile stresses are present. And then once we come back, it gets blunt. Here it gets blunt, and then once we remove the load and then becomes zero, or once we go to negative, the crack becomes sharp again. It goes to the original position, whichever the position it was present.
Okay, thank you. Clear.
So, yeah. So if we have, in order to avoid the fatigue, in order to improve the life of any fatigue material, you should make sure that the surface doesn't have any cracks. For instance, if the surface is not having any crack, then to initiate crack itself, where the crack initiation will take place, that itself will take more time. But if you already have cracks or small cracks present on the surface, it will get easily, it doesn't, because we need more energy to be spent in crack initiation rather than crack growth. If the crack is already present, then we don't need much energy to get it propagated in either stage 1 or stage 2. So when you guys are designing, make sure that the surface finish will be having the roughness less than 0.2 microns, so that the surface will be smooth, and then it will be having more life, especially where there is a fatigue, chances of fatigue loading will be present. So that's one thing how you can avoid, and the microstructural variation also can be done. So I hope this is clear now, right? If you guys have any question, we can still discuss. It's fine.
Ma'am, I have a question, ma'am.
Yes.
You are specifying that the failure will be in brittle fashion. So can I understand that all fatigue failures will be in brittle fashion and there is no ductile failures at all?
Brittle failure. What is the question? Like all fatigue failure will be happening by brittle?
Yeah, you specified sometime during the discussion. You specified that it will be brittle failures after when the crack initiates and
Yeah.
While failing, it will be by brittle nature. Am I right?
So, but still, if the sample wasn't ductile enough, then it could have been easily broken. The plastic zone wouldn't have been there, and the crack blunting wouldn't have happened. So it will be keep on propagating without further blunting actually in the material. That is the reason, and we will be having enough time to at least when we keep on doing NDT once in a while, and then we can observe that there are cracks present. It is forming, cracks are forming, and either we can replace the material or we can take necessary actions. So yeah, finally, even though if you see the fracture in terms of like in a brittle way, having ductile material actually helps you out a lot, so that the crack blunting will happen and the stress concentration gets reduced at the crack tip. So both place, even though the crack will be very big inside in that, once it becomes big enough, then only it will be failing in a brittle manner, because it will not if half of the material, if half of the surface is having a free surface and it is having crack, and then it doesn't have need much time to propagate further, right? You got the point which what I'm trying to say?
Not fully, ma'am.
So like I'm trying to say that, yeah,
So,
you can say that it. Yes.
hello.
Yes, hello.
Yes, not fully actually. Should I consider that it fails by brittle, or there will not be any ductile failure at
You can
all
say
in fatigue?
brittle only, because
Okay.
you can say it brittle only. It is failing. Fatigue will fail by brittle only. Yes, you can say that it will fail by brittle. But you should have some amount of plastic deformation so that you will be having a warning or so. Yeah, but yeah, you can at the end it will fail in a brittle manner. Yes.
I have an example, ma'am. Actually, I came across fatigue failure recently. It is a stainless steel. Actually, it's a 3 thickness plate.
Okay.
So actually, I don't know whether it's brittle or ductile. That lab test was not done. So I'm just trying to correlate between today's class and that incident. So
Can you tell me what exactly happened for this one?
actually, it is a 3 thickness plate in a pressure vessel, a vertical pressure vessel.
Tube
It's like a
pressure vessel,
compartment.
right?
It's a vertical pressure vessel.
Which pressure? Can you repeat again?
Pressure vessel, which
Pressure
is
vessel. Acha,
mounted.
pressure vessel only. Okay, not tube. Okay.
Yeah, it is mounted
Okay.
in vertical direction.
Huh?
Then there is a compartment that separates the top and bottom portion, and this compartment, there is a plate welded that
Is
separates
this
the
something like
vessel.
this? Pressure vessel. I'm expecting
Yeah,
something like this. And then there is some compartment to that will this is a compartment that will separate the tube, I mean pressure vessel, and then okay.
yeah, it's at the mid of the vessel. Just a
Huh?
plate, a circular
Okay,
plate
okay.
at the mid of vessel. And there is opening at the center of this plate, and
Huh?
the gas flows from bottom to top
Okay.
to this annular plate, I would say annular plate. Yeah,
Okay. Okay.
yeah. And there is a beneath the annular plate there is a beam welded just to support.
Okay, welded. Okay, welding has happened.
And this welding is through stitch welding. It's
Okay,
intermittent welding
stitch weld.
and continuous
Huh.
welding.
Okay.
So in two cases, we have seen that the at the corner of stitch welds, the crack has initiated, and
Huh?
it has resulted. It has developed into through thickness crack, and the leakage starts in the pressure vessel. So our team came to know about this leak,
Okay,
and
can you tell me where was the crack on the this one side or near the weld? Where was the crack?
it was initiated at the edge of the stitch weld.
Stitch weld.
Yeah.
Okay. Can anyone answer what can be the reason? Like what are you guys thinking?
So, was that the crack initiation from the toe of the weld or from the crater? Did you do any investigations done on that?
From the toe of the weld, from the toe of the weld, yes. So to add to that, actually, it was noted that there is a variable flow or fluctuating flow of gas.
Huh?
So possibly this is
It cannot be fatigue. I don't think so. Fatigue is involved here. Like I understand that you're confused a little bit regarding because the stresses are involved, and then maybe flow variation will be there, and then stress variation can be possible. But as you're telling, weld need happen near the weld, and you have to understand there is one more point. The pressure is also varying throughout the specimen, like throughout the pressure vessel, not just near. Why it started there only? If I'm not wrong, it was because of welding only it happened.
sorry, ma'am. Actually, the pressure is not varying because it's a pressure vessel, so it is nearly 1000 psi. So it is throughout the column, throughout the vessel, it's same pressure.
And what was the other material welded with? Both were the stainless steels of the same grade?
Yes, 321, yeah.
Both were 321 and 321.
Correct. Actually, it has been verified as static cracks, but what I'm trying to understand is whether this has failed through brittle or ductile. So since the material being assessed, so this is what I'm trying to relate. So sorry for taking more time.
No, it is fine. Like one thing for sure, it is because of welding. Something is to do regarding welding. And then if I'm not wrong, like even unless until we see the sample and we'll not be able to understand what exactly is happening there. And then it was 3 mm, so I'm expecting it. They might have done the stitch welding in one pass only, not in multi pass also. And the thing like and like you have to see where the crack has initiated, and you can correlate using that, like even the stresses will be present in the weld also, and if they have done any heat treatment or not, they have relieved the stresses or not, that you can see, and what is the history of that, and how the crack is propagated. Like first try to find out where is the crack initiation or origin point, and then see the pattern in which it has propagated. At the end later, yeah, I got the asking question why you are asking regarding brittle manner, whether it is possible or not. Like and as per my knowledge, like this is for sure because of the weld only. No, you probably have to concentrate more on weld rather than fatigue.
Yes,
Any temperature is involved in this case?
temperature is really less. No, actually, it is around not even 250 degree Fahrenheit.
50 degrees.
250 degree Fahrenheit.
Degree Fahrenheit, 200 Fahrenheit. Okay. Degree Fahrenheit, okay.
Okay. So did you perform this fatigue test also?
No
Endurance
test has been performed. No test has been even what we have done is we have just rewelded it actually up the grounded and removed the cracks, and it has been rewelded. So
one question actually, this is in service condition or newly designed component or sorry, this is in service condition, this pressure vessel?
Yeah, it has been in service for more than 8 years.
More than 8 years. 8 years now you have observed the crack actually, right?
I think if I'm not wrong, they might have observed very big crack. That's the reason why he was asking whether it is brittle, it will fail in brittle or not, right? They might have not the smaller one.
The width of the crack is around say may not be more than 5 inches.
5?
5 inches.
5 inches, sir.
Not more than 5 inches, yeah.
5
It is
inches means
bigger than
very high.
Yeah.
I mean the width actually. Maybe giving a higher value. Maybe it will be 3 to 5, I would say.
Okay, yeah, 3 to 5 inches. It is very big actually. That is true. Like maybe initiation can be the reason for initiation can be welding, and further probably it might got propagated because of stresses or for sure, and then some maybe corrosive environment also will be present. You have to do the analysis, EDAX analysis, in order to understand what type of product you have present on the surface, and then or OES also, like anything compositional analysis, and then you will be able to relate whether corrosion, because of corrosion it happened, if any corrosive environment, or just because of the
It's not,
stresses that are
sorry,
present.
sorry to interrupt, ma'am. Actually, there is no corrosion. Actually,
There is no corrosion. Okay.
no corrosion. It is.
But I doubt that fatigue. Does anyone think that fatigue can be involved here?
I'll tell you, ma'am. Actually, we refer to APA 571, where there is a clause on fatigue, and they have specified cyclic flow conditions or kind of vibration.
Okay.
This plate has a little bit vibrated actually, so that could have caused probably the fatigue. But as I said, I just want to. I was interested to know whether it had.
Okay, it is
failed
fine.
by-
Chances are there it can be fatigue also. Even the small amount of loads also can be there, and then 8 years is not small amount. Like it might have enough time to do, and if there are no if there are any stress concentrated regions also because of welding or for any other for that matter, and the temperature is also high actually, like 120. What is the material again?
SS321, ma'am.
Oh, stainless steel only. Yeah. So sensitization chances are very less, but still the creep can also happen. Like even though it is not very high temperature.
So what are the
Can be-
vibration levels? Any idea?
It can be not
You
possible.
said that the pressure vessel is vibrating. What is the level
No,
of vibration?
Not pressure vessel. The internal, which is the plate, which is another plate. No? That only was vibrating, but we are unable to estimate what is the vibration.
Okay.
Okay. So if you want, you can share
If you put-
few of
yeah,
the images or
if you put-
something. Next
Yes,
class.
If you put in
Okay.
it and clearly defined, maybe we can help you.
Sorry, ma'am.
Yes.
Actually, the things is settled actually. Okay,
Achha,
but I will not be able to share it because it's official. So
Yes, I understand.
Okay.
So if you want to discuss more also, we can have a discussion regarding this. It's fine, but you just let me know before by next class so that I'll allot 5-10 minutes for you, like if it's required for to do some discussion regarding this more.
what I will need is only thing whether brittle
At
or
least
ductile.
if
That's the only thing.
yeah, brittle or ductile, if it is very 5 to 3 inches, right, it is a brittle failure. Initially it might not, the reason for this initially it might be very small crack. It can be because of stress corrosion or anything for that matter, or surface roughness might be not fine. That's why the cracks might have initiated, whether it can be because of stresses also present or fatigue also, anything. Initially it might be because the reason can be fatigue corrosion for anything for that matter, and then later on because the crack width is 3 to 5 inches, so it is very big. So finally, it is brittle failure only. That is for sure. It's not ductile failure. And then for that to confirm, also you have to see the surface. What are the features on the surface? Then only we can confirm regarding that as well. And features. Remember one thing for sure. When you're doing the feature analysis, the features can be deceiving because like it might have cracked a little bit earlier, and once it gets exposed to the oxygen, the corrosion also can happen. So it can be in such a way that you might think that it is because of corrosion also. So you have to make sure that like it is fresh sample or something like that. But yeah, it is a brittle failure, like because the length of the crack is very high. That's why.
Okay.
And also the welding, how you are performing the welding, maybe because of the residual stress, the beam stress will increase. So the life also will be reduced.
This is only 3 years, so we need not like bother much about the residual stress and I don't think like
welding location at the welding.
That's only I'm telling, like
During
as
the
it
welding process.
No, who is telling this? Like we shouldn't worry about the stresses. Who is telling this?
Alfred.
No, I don't think so. That is true. Like, see, even for initiating the crack, even for small crack, also whether it can be in micrometers level, micrometer range, those small stresses are more than enough. 3 mm is very big actually. So once it gets initiated, further propagation will be easier. That is what I'm trying to say here also. Crack initiation takes more time. In addition to that, if we have any stresses along with that, it gets easily initiated. And if the surface is also not smooth or anything, then it will be very high chances that crack initiation can happen. Once it reaches minimum length also, then crack growth, the final failure will not take much time. So you cannot ignore just thinking that it is just 3 mm and then residual stresses shouldn't matter much and all. I don't think so. That's a valid thing.
It's because of an
Can I add
intermittent.
one thing, ma'am, here?
Yes.
To add to Mr. Alvin's point, actually, the pressure vessel standards doesn't even call for postal heat treatment for stress relief.
It not go for heat
for
treatment, for
stainless
post
steels.
heat treatment.
Yeah.
No.
For stainless steels, it doesn't require it. But whereas for
No, that-
thicker steels, ferrous steels, they are mandating the postal heat treatment to relieve the stresses. But it's not so for SS. So in one point of view, Alpin's view is right, is what I feel. But I may be wrong also. Maybe you have to confirm.
And particularly what I meant is because it is an intermittent weld, intermittent fillet weld. So like no much what do you say importance, like importance in the sense like, and moreover 321 is a stabilized stainless steel grade which has like the fracture toughness is very high when
Very
compared
high.
to other
Okay.
materials. So in
I
that
got
case,
your point, like why you're telling that it is not important, but we cannot neglect that actually.
all right.
So, fine.
Yeah, can I add one?
Yes, sure.
Yeah. So just I was listening to the discussion. So even a lot of thoughts about brittle failure and ductile. Just what I can think of is that when we call it as a brittle failure, it is
Mhm.
I think basically it comes to a failure in which the material doesn't exhibit any visible plastic deformation.
Correct.
And if it is a ductile material, I believe the mode of failure will be yielding.
Yes, yielding will happen.
Yeah.
Correct.
Whereas, so then if it is a ductile, purely ductile material means yielding itself is considered as a failure, and we won't wait
Yes.
for any fracture or anything to happen. I think the
Correct.
main reason why we are studying fracture
All
mechanics
this.
is because ductile materials failing in a brittle fashion. The reason could be
Correct.
many. So,
Correct.
and another thing is that as many of us, discussed about welding and heat treatment. So, see, the thing is, I don't have experience on stainless steels, but then aluminum alloys, which are used on, aircraft for reducing weight and high strength to weight ratio.
Yes.
Everything is in a heat treated condition. Different levels. It will be solution heat treated and naturally aged or artificially
Yes.
aged, etc.
Uh-huh.
So when you do this heat treatment, basically the material loses its that the material does not exhibit a appreciable plastic deformation that you can see the deformation has happened. Rather, it will fail in a that what happens is that the ultimate stress is more critical. So we classify in something called as a yield critical and a tensile critical, ultimate tensile critical. So if when we design any repair or anything like that, suppose
Mhm.
based on the material which we are using for the repair, like a doubler or a patch or anything,
Mhm.
so aluminum alloy itself, based on the heat treated state T4, T3, T6, it can
Mhm.
be either yield critical or it can be either tensile critical.
Mhm.
So if the so what we consider is that 1.5 times the yield strength
Mhm.
and the ultimate tensile strength, whichever
Mhm.
is lower, we have to take. So for example, if
Yes.
1.5 times in yield strength, if it is
Mhm.
lower than the ultimate tensile strength, then we call that material as a yield critical material. Whereas
Correct.
if the ultimate tensile strength is less than 1.5 times the yield strength, then it's an ultimate tensile strength critical material, and it will fail by crack and ultimately fracture. So yeah, just to add to the discussion.
Yes. Whatever you said is all valid points actually. So yeah, here you have to observe one thing is for sure. See, aluminum, no matter what they are doing heat treatment, because Ascas aluminum, if I'm not wrong, they have a lot of dendritic regions, interdendritic regions, and then inclusions and segregations also. So if we extend the same thing here, even in the welding, like yeah, it means it will be melting as well as solidification will be happening. So in this weld region, the microstructure will be entirely different compared to that of here non-weld, and even it will be having heat affected zone also. We shouldn't forget that. So heat affected zone, chase it. So, and then this will be weld metal, and we don't know what treatment they have done to base metal previously. Consider it is cast only. Still, there is a variation here. There is a weld metal, and then there is a heat affected zone, and then there is a again cast a zone. So, stainless steel microstructure, whatever it can be. So, so variation in microstructure again induces a lot of stresses inside the material. So heat treatment has to be done in order to avoid these type of failures. So that is one point that I wanted to take from they. No matter what they do, heat treatment for sure for this aluminum. So that's one thing.
Yes,
And
madam. Mr. Arjun has nicely added. Madam,
yes,
just to
yes.
please try to conclude this because no, we may be running short of time.
Yes,
I think
sure.
this
That's it. Like crack initiation will be there. Crack growth, it will be happening in two stages. Where first stage, where high shear stress will be acting. In second stage, high tensile stresses. And then once it reaches the enough, and then of course blunting. Again, the crack gets sharp because of the unloading again happening. It go back to the initial stage that was present, and then the cycle keeps on repeating in the similar fashion. And once it reaches the enough stage, and its final failure will be happening in a brittle manner. So, yeah, we will start with the questions, and you guys also saw the striations. Along with that, you guys even saw one example of my photographic image of real life failure that happened, where the crack started from where the stress concentration region was high, where there was a step here, and then the crack initiated here, and then further striations and the beach marks were present, and then the crack got failed finally. So that is one thing. And now we will start with another questions like assignment question. This is assignment 3. Question 1. Austenitic steel gets corroded due to penetration of due to precipitation of chromium carbates along the grain boundary. This corrosion mechanism is known as. I'll discuss each and every point. Hydrogen embrittlement. Sir has discussed about hydrogen problem that where hydrogen will be happening. Like I want to say one thing. How much like we all know that hydrogen atom H plus ions are very small because it has only one atomic number as one, and then they will be very small. So when there is an hydrogen atmosphere purposely kept, or like when there was Sir gave two reasons where hydrogen is actually purged in order to remove the oxygen, or in that case we'll be purging hydrogen purposely, or hydrogen which is already present, whether it can be in pressure vessels or any other things. If hydrogen atoms are present, the diffusion of hydrogen atom inside the material will not be difficult, because the size of the atom will be very small. The diffusion gets very easy, and as we all know, most of the materials is no perfect, and if it has any voids present in the material, the it will be hydrogen atoms will be attracted to go to that region. So if I enlarge this void, hydrogen atom, each and every hydrogen atom will be attracted to go to that voids. And then once it goes to this voids, as it has an electron and it can form a bond, and H2 formation is possible. And once the H2 is formed, like it will be having a lot of pressure built up inside the material, because H2 we know that it is a bomb, like, and it will, in order to remove this pressure, all of a sudden it gets it behaves as if like a whole thing material got ruptured because of like brittle manner because of this hydrogen, and this is called hydrogen and hydrogen, what is that embrittlement happening. This is also, there is also one more point where I have to tell, uh, if this is not happening, and consider Fe2 plus ions or iron or any other atoms are present, and it forms iron hydrides of iron, or hydrides of any alloying elements that are present inside the material, and these hydrides will be very hard and brittle, and that's called hydrogen embrittlement. because the material it was supposed to be the whole materials were supposed to be a ductile material, but because of the hydrogen present or because of diffusion of hydrogen atom that easily gets happened, and these hydrogen creates hydrides, and these are brittle in manner, and then on when the brittle material is present, the crack propagation through the brittle material will not be that it doesn't require much energy, and also it doesn't require it will not be doing crack blunting will not be happening. So any stresses that are present, it can easily form cracks. It can go through the material, even though the hydrides are forming only on the surface. Yeah, even if it forms a smaller, very small initiation crack initiation, and the further propagation will not be that difficult. So that is called hydrogen embrittlement. And creep fatigue, as we know, like creep will be happening. Can anyone tell me when the creep will happen? So that is one thing that I wanted to discuss regarding hydrogen embrittlement. There are two different types, like two different ways it can happen. One, it can diffuse to voids and form H2, and then crack burst open the whole material as if it was behaving in a because the pressure gets built up inside this void, and because of the formation of H2, it will be breaking in brittle failure, because pressure will be very high that the material will not be able to withstand it. So that is one way. Or it forms hydrides, and then the crack propagation gets easily formed. So that is hydrogen embrittlement, how the hydrogen can cause failure in the material. And can someone explain me what is creep?
Creep is time and temperature dependent deformation.
Temperature dependent. What are the things that are required? Time and temperature.
Yeah, load.
That's
Yeah.
it. Yeah, obviously load is there. Without load, where you will go? So some amount of, even the load applied is very small. So you can consider I had a very good example for creep. I forgot. It was present in our daily life. I'll probably tell you in the next class. So even in the old things, if you see, without applying any load, like if you apply very minimal load, even if you just keep the a small amount of load on the sample, the material loses its property, especially when you the temperature is very high. It is above 0.4 to 0.6 TM. That is, TM is melting temperature, especially when it is above 0.4 to 0.6 melting temperature. The small amount of applied load, even it can be below this also, but still, like we are considering, creep will be easily seen when the temperature is very high. And small amount of load applied, it doesn't have to be fatigue, like variation in load, and the deformation you will be able to see. And this deformation, creep fatigue, like when there is a variation in the load, like some amount of variation in load is happening, and then the it gets easily fractured, because even though the load is very low, the with lot of time, I mean, for longer time, the fracture will be happening, because the time temperature and load is present. The main reason for creep to happen is temperature. And instead of having consider some particular length, because of the temperature and the load, it is already present, like it will be creating little bit higher dimensions. And variation in dimensions is also not good thing in our material, that we already know. So can anyone tell me what is active path dissolution?
Cracking along the grain boundaries.
Why, I want to ask you one thing. Yeah, there are grain boundaries, and why the dissolution will happen along the grain boundaries?
They are the weaker regions.
They are the weaker regions.
Precipitation. Because of
Yeah,
precipitation.
Who said they are the weaker regions? Has anyone done the etching of microstructure? Or anyone saw them, like anyone has done personally?
in college, yes, ma'am. We
Huh?
have a lab. No? In college, we have lab. Yeah, so we have done.
Yeah,
Labs,
anyone has
yeah,
done
correct.
polishing and then etching. And we, in that etching, what we do, can anyone tell me?
it's we are applying acid, slight acid to expose the grain boundaries.
And why that acid or whichever the etchant only attacks the grain boundaries?
I don't know, ma'am.
Can anyone tell me why it only attacks the grain boundaries? Why not inside? Like even inside there is a material and you're not selectively applying only on the, you are putting completely in the inside the acid, right? Inside that mild acid. So when I say acid, don't think it is a strong acid. It's a very mild acid.
Yeah, somebody said it is the weaker region compared to the.
It is a weaker region. Why it has to be weaker region? Like if the precipitates are there and you apply the load and just locally you apply the load and near the grain boundary and locally apply the load only inside the grain, you think so that this will be having, it will be behaving like it will be having weak, the strength of the material will be less there. You think so? If you just apply only on the grain boundaries. Or if you just apply inside the grain, you think the strength of the material will be higher here or here? That is not the reason. It is not a weaker region. It is not a weaker region. It's a wrong answer. It gets attacked because the energy that will be present here, it will be having higher energy stored compared to the inside material, not because that is weaker region or anything. The compared to inside the grain boundary, the inside the grains, the grain boundary will be having higher stored energy compared to that of this one. That's why we etch in such a way, we give in such a way we do the etching so that it only etches the higher energy region, not inside the grain. And the same thing happens even in active path dissolution because they are very high region. First thing, when you, for instance, even when you see the ice cube, can anyone tell me which is the region that it gets melted first?
Bottommost.
So, this bottommost.
Bottom. Yes.
Why?
The core of the ice, the core.
This is 1, 2, and 3. This is 1, 2, and 3. And tell me which one will get melted first. Try to imagine keeping the ice cube outside the fridge, and which one will be which one starts melting first?
Corners.
Yes, exactly. Why corners?
Surface area is less.
Exactly. Surface area is less because every time an atom will be having considered it as a 4 bonds. So inside material, inside the bulk one, it has 4 bonds. And then on the surface, one of the bond is broken on the surface. So it will be having 3 bonds. And this is on the surface. This is on the bulk. And near the edges, these are edges. So it has only 2 bonds there. And near the corner, it has just small amount of like any other bond that are present here. So here one it is present, here one it is present, but then it will be exposed more at the corner compared to the edge. So it will be having higher surface energy. It wants to bond with something so that it becomes stable, or if it is not, when you're trying to melt, if you're trying to solidify, this is the place where it starts solidifying first because it attracts the bonds very easily and then it is very ready to form a bond and then keep growing. But then when you remove, keep it in the outside, when you keep it in the room, then it will start dissolving from the corners because it has high surface energy. And then the edges starts dissolving and then starts the surface, not the bottommost. In the similar way, when you do the etching, the way the high concentration, high surface energy will be present, it starts attacking and then dissolving more compared to that of inside the grains. Okay, is it clear? In the similar way, the active path dissolution also will happen along the grain boundaries, because the surface energy, the energy stored inside the grain boundary will be higher. And then corrosion fatigue we already discussed in the last class. So now you tell me the answer for this. Austenitic steel gets corroded due to precipitation of chromium carbides along the grain boundary, and this corrosion mechanism is known as?
Active path.
C, active path dissolution.
Active path.
Are you sure?
Yes.
Yes, ma'am.
Yeah, it is true. Why are you guys taking so much time to answer? So ferritic irons are more susceptible to dash. Hydrogen embrittlement, film induced cleavage, active path dissolution, creep fracture.
Hydrogen embrittlement.
And can you tell me why?
Because rusting will form. Rusting, there is a possibility with hydrogen.
In austenitic irons will not form rusting.
Once this hydrogen gets entrapped,
Mhm.
these hydrates may form in the form. Chances of formation of these hydrates is more with ferritic irons.
Why? You are almost approaching the answer. Can you tell me why?
No.
I have one question, madam. Ferrite iron, this is means cast iron, right? This is not
It doesn't have to be even
austenitic
ferritic.
steel.
Mild steel is a ferritic iron.
This is not austenitic steel, right? No.
Mild steel also can be ferritic steel. Okay, that's the reason why I had kept few things, like a few up to 0.022% of carbon is called ferritic steel. And if it has up to 2.14, it's almost like 100 times, like 100 times, then it is called austenitic steel. Can try to correlate this point as well as the point that I said that hydrogen can easily dissolve inside the material, and then try to give the answer like
Because the
ferritic
carbon
steel.
percentage is very less.
Yes, because
Okay,
the
it
carbon
is
percentage. Yes, tell.
whatever carbon is there, that is only giving the strength. Okay, that is eaten away by this hydrogen, it becomes weak.
Hydrogen, it will,
Yes.
hydrogen it will generate some pressure in the grain boundaries.
Okay, so carbon here, you can see that amount of carbon that is present in the ferritic steel is very low, and then it means that many interstitial atoms that will not be filled by carbon. But here you can see that as you can see, I'll show you one more thing. I forgot to. So as you can see, most of the carbon atoms which will be present in alpha steel will be present in interstitial places. So if the carbon amount itself is very low, many of the interstitial atoms will be empty. So the hydrogen can easily dissolve inside the these interstitials, and it can easily sit in these interstitial atoms. But in the case of iron, austenitic steel, carbon amount is very high. So all the voids which will be present will be filled with carbons. So it will be having very less amount of space left for hydrogen to get diffused. So that is the reason why ferritic steel will be more susceptible for hydrogen embrittlement compared to that of austenitic steel. I hope you got the point. Does anyone have any doubt in this?
No, it's clear.
It's clear.
That's the reason why I
have
explained here regarding hydrogen embrittlement. Yes.
Ma'am, why not creep, ma'am?
Huh?
Why not creep?
Okay. See, we are not just talking about it is more susceptible to. What can be the reason that austenite cannot creep? Why austenite cannot creep?
Okay, because in my opinion, the austenitic stainless steels have a higher temperature resistance and it can be used till more than 1500.
Okay, so here
and-
again, I'll come back again to the So fine, even if you are increasing the temperature, consider we are working around 900 degrees Celsius for creep, okay? So when we are going in the phase diagram, you can see that. 1 second, give me a. So, you will not admit. So even if you're working around 900 degrees Celsius, the ferritic steel will go to austenitic steel. So, and consider we are working both ferritic steel as well as austenitic steel at 900 degrees Celsius only. So if when you go to 900 degrees Celsius, ferritic gets converted to austenitic phase, and then austenite will still be in austenite phase only. So like how there will be variation in creep for austenite and then ferrite.
Ma'am, I can explain one thing, ma'am, actually.
Yes,
The
yes.
limit, the threshold limit for creep for carbon steels are around 750 degree Celsius. Whereas
Yes.
for stainless steels, it's much more, maybe double times of this one. I don't know the background and
Yeah, austenite will be
what you
having
explain.
main can you tell me one more thing, like austenite will be present at the room temperature as austenite because we add manganese, nickel, cobalt and copper. Those are austenite stabilizers. So this, when you add these things in the austenite, and even at the room temperature, they will be behaving like an austenite only. So when you alloy with this much, then the creep resistance will be higher because of the precipitation and then solid solution strengthening happening, all these things. So that's
Yes,
the
ma'am.
reason why austenite will be having higher creep resistance compared to that of ferrite. But then is it more susceptible to, but still ferrite is ferrite, like it will be having higher resistance to creep. You just, when you keep the creep, the variation between these two will not be that much. But when you keep as an hydrogen embrittlement, it will show visible differentiation between austenitic steel as well as ferritic steel. So that's the reason why sir was telling also in the one of the lecture, if whenever there is an hydrogen embrittlement, go for austenitic steel rather than normal mild steel or ferritic steel, stainless steel.
Yes, ma'am. Okay, noted. Thank you.
Can anyone describe me film induced cleavage? This we haven't discussed. Yes, I'm not discussing. I want someone to discuss this.
Yeah, actually, yes, from the SIRS lecture,
Yes.
if there is already there is a crack into that, uh, these materials will enter, this corrosive materials will enter, and that
Correct.
leads to further corrosion.
Yeah, that's all. Here it can be oxides or hydrides or chlorides or anything for that matter, etc. So this will be again brittle in manner, and then once it gets formed on the surface, and as it will be brittle, so there will be no plastic deformation will be happening again. So further easy growth of crack will be possible. So that's the reason, that is film induced cleavage. Okay. So the right answer for this is hydrogen embrittlement. Local chemical attack is precursor for stress corrosion cracking, creep, liquid metal embrittlement, corrosion fatigue. We have discussed about stress corrosion cracking. We have discussed about creep. We have we can discuss about liquid metal embrittlement, and we have discussed about corrosion fatigue last time only. Like we have discussed, and we had a little bit debate also regarding that. And first tell me the answer for this, and then we will discuss further.
Metal, liquid metal.
Sure, right? So what is liquid metal embrittlement?
Is a film induced.
Yes. Whether it
There will be the chemical action, chemical reaction, right?
correct, there will be chemical reaction because of some metals present on the surface. This it will. I'll show you one of the example. So when you coat steel with zinc coated, you'll be having failure in a the toughness of the material will be very less. But then for the similar material with uncoated zinc, and when you don't coat it with zinc, it will be having higher strength. And then as they also observed that the fracture was happening, it was very visibly seen. And this is mainly because what happens, particular metal like lead, mercury, zinc, tin, or all these things forms, it forms a compound along with the product that is present, just like hydrogen embrittlement, how it happens. It dissolves the material that is present under, and then it either forms another product and which will be in brittle manner, or it even removes the surface. As you can see here, some amount of discoloration has happened compared to the base material. So, and then it will be either product will be brittle, and the further crack propagation will be easier. And as you can see, some carbides, zinc is present morely in that region. And or it will be because of like it will even dissolve the whole metal. So that is liquid metal embrittlement. So local attack, it will happen very locally. It will not be like throughout the material and all. So local chemical attack is mainly because of liquid metal embrittlement. So embrittlement, wherever you see the word embrittlement, you consider that it is forming brittle product. Even last time also we saw hydrogen embrittlement similarly. So question 4, assertion is surface treatment has to be conducted with extreme caution. Any unnoticed crack on the surface can induce corrosion cracking. Both the statement are true, and statement 2 is the reason for statement 1. Both the statements are true. Statement is not, sorry, I'm previously. Statement 1 is the reason for statement 1, and statement 1 is not true, and statement 2 is true. Both the statements are false. So what is the answer for this? Just I'll give 30 seconds and then
Both are true,
both are true. That's perfect. Nice.
and one is the reason for true.
One is the reason for
One is the
two.
reason for statement 2.
Yes. So your option will be B, right?
Yes.
That's right. So surface treatment has to be conducted with extreme caution so that like it will not form any surface cracks or anything. If it goes unnoticed, the surface cracks on the surface layer can induce corrosion cracking. This, as sir already explained this part very nicely in the. So we will move on to next question. For a thin plate with a central crack in a fixed grip, the strain energy varies parabolically as the crack grows, varies linearly as the crack grows, varies exponentially as the crack grows, remains constant for any crack length. First, let's see the equations, and then we can say whether it is varying linearly or parabolically or anything. And as we all know, like when the strain energy is present in the presence of cracks with length A, that will be having so this is sorry, this one is previously one. So, and then what will be the strain energy? Like, I want to discuss one thing, like, we apply load and then strain energy will be formed around the surface. And then in order to create a new surface, strain energy will be used to create a new surface. So strain energy get reduced and then it converts into surface energy. The energy that will be having to create a new surface, that is surface energy, and corresponding to that will be having.
Madam, just to please repeat, the surface energy and strain energy,
Yes,
are
yes,
they
yes. No,
interconvertible?
I am just writing down the equation, and of course I'll repeat it again, and I want to discuss a little bit more also regarding this. First, this is the equation for strain energy that is stored inside the material, right? When we are doing like normal, when we are applying load, sorry, load versus displacement is happening. some amount of strain will be present, stored inside the material, and this strain energy will be theoretical strain energy. But when the crack is present, the strain energy stored inside the material will be depending upon the crack length as well as the thickness of the material, that is B, thickness of the sample. So this is the strain energy correlation when the crack is present, and when we some amount of strain energy is stored, and in order to create a new surface, like for instance, as I discussed here, the ice cube 1, we saw that it started melting from the corners because it has high surface energy. So if I have to that is the surface energy was higher at this region. So when two atoms are bond together, in order to break that bond, we have to provide some energy. Or even if you put another atom here, in order to create the bond also, it gives out like it requires energy both to create a bond as well as to break a bond. Some amount of energy will be required. So in the similar way, if you have to create a new surface, that is when the crack is present inside the sample, and then we know that when we apply a load, not just the plastic deformation is happening, but also some amount of new surface is forming. Like there will be one surface as well as there is also another surface at the bottom, one surface at the top layer and another surface at the bottom. So we are actually breaking the bonds between the atoms that are present near the crack tip. So in order to do that, break the bonds, we need some energy. That whatever the strain energy that was present inside the material, the total energy, whatever that was forming, is the strain energy that are present as well as stored surface energy. How much surface energy will be formed because of the like how much the surface energy is formed, and this is strain energy. This will be negative because we are it will be forming, and then this is positive because we have to give that much amount of energy to create the surface. So as we all know, with surface energy with with varying the crack length, it varies linearly. It doesn't have any power or anything. So at the same time, so I'll just draw the energy curve which sir said, and I'll be just discussing the same thing but with little bit more detail. And this is energy curve. And so for surface energy, it will be positive. We need to give some amount of energy to create a surface. You getting the point which I'm trying to say?
Yes, yes, yes.
But whereas the strain energy will be in negative. So it was in negative direction, right? Strain energy. But when you add these two, initially the surface and initially as surface energy is positive and this is negative, initially it increases and then it decreases. This will be the total energy, right? If I'm not wrong, total energy only. And there is a point where below this, there is an incremental way, and here it is a catastrophically. So where there is a point where the slope is 0 is the point where like we will be considering that is the important thing for us and for even for fracture mechanics. And this is the point where we see maximum what is the strength of the material or anything for that matter. We will be considering which are at this point only where the slope is 0. So it means that we have to differentiate total energy with respect to A and then consider it to 0. So when you do that equation, that's when we get the fracture strength. So this I wanted to discuss. Yeah, I just wanted to make a points clear here. That's all, few points, because most of the questions are based on this. So as we saw that this will be, we will even derive this, and I'm considering that B is 1. unit thickness. And as we know, this is negative because it will it will be producing, and then strain energy that is formed will be positive, and then that will be 4A, and B I'm considering it as 1 gamma S. So when you this will be total energy. I'll just try to do it in here. This is right? This is surface energy for creating new surface, and then this is amount of how much we are giving
Hello?
the stresses. Yes, yes, yes. Hello? Can we do it? And this is in negative 2 pi A sigma square by E plus 4 sigma. This will be in negative again. So when I send this to other side of the equation, 2 pi A sigma square by E is equal to 4 gamma S. And this is fracture strength. Because we are considering where UT is 0. And this will finally will give us S by pi A.
Madam, where it UT is 0 or slope of UT is 0?
Slope of UT is 0, this one.
Okay.
So we are equating UT to 0, and we are also considering B is equal to 1. The thickness of the material, is unit. Okay, and that's how we get the derivation. By considering here, because this is the slope of the equation, and the surface energy will be positive because we have to give some amount of energy to create the surfaces, but whereas the strain energy will be negative. And also when you the total energy will be the surface energy plus strain energy of the material. And when you plot total energy, we will be having a slope something like this, and here it will be in incremental way. And once it reaches above the slope, when the slope is equal to 0, and then it will be failing in a catastrophic way. So we have to see where fracture toughness is slope is 0. So that's the reason even the fracture stress and all will be calculating based on that. So I hope this is clear now for you guys. Now, if you guys have any doubts, you ask me, and then further, most of the questions are based on this. So I want you to be able to answer properly.
Fracture strength formula, just can you show me once? Shows.
Yes. I hope this is correct because we just derived this. Yes,
Excuse me, ma'am.
Yes.
Just that, when you drew the graph, strain energy, that slope is slightly different, I think. It reduces gradually, and it's like a parabolic, but this is like an exponential drop, no? It should be like it, about what to say. I just know the graph which was shown in sir's video.
It's the same graph that I drawn here.
No, the strain energy graph is slightly different. The slope.
Yeah. I remember this. It was parabolic and it was.
Yeah.
Okay. Yeah. I forgot this. Yeah. Thank you so much.
Yeah, welcome.
This was strain energy. Yeah, that's why it increases and then decreases. Yeah, it was not.
Correct.
Noted.
Yeah.
Correct. Thank you so much.
Madam, there is a doubt. Okay, if in the question, if it is says actually this formula, no, whatever formula you told, for
yes.
Hello.
This is the formula.
Actually, if it is thin plate is considered.
This is plane stress.
Yeah, plane stress condition.
Yeah, we will not go to plane strain for now. Like that is a formula anyway. It is present. I just derived in plane stress condition only.
For suppose in the data, if it is given that Poisson's ratio is given, then
Huh?
which need to be considered? Actually, Poisson's ratio is given. It was told that it is a thin plate. Still, we can go with the plane stress
No.
condition.
If it is given, it is just to confuse you. That's all. Like,
That's all.
if
Okay.
Poisson's ratio, even if it is given, and if they're saying it is plane stress, so it
It
means
was
that
not told. It was not told clearly that it is a plane stress. It was told it is a thin plate.
thin plate means it is a plane stress only. That is just to confuse you.
Okay. Okay.
But still, I have to see the
Ma'am,
question properly.
No,
I'm
it's possible just to please see.
Huh.
Because many questions are framed on this.
Yes, I understand. So now you answered me the question for thin plate with a central crack in fixed grips, the strain energy varies parabolically, right?
Yes.
Now you got the how the parabolically this is the strain energy that is varying parabolically. And thanks for like I don't know who corrected me, and thank you so much. Yes, it will be having the slope in towards the y-axis actually, and this is a square. It is in a square is in x-axis. So for thin plate with a central crack in a fixed grip, the surface energy.
changes linearly.
Linear.
Perfect. So, which is the correct expression relating the fracture strength and surface energy in the case of brittle material when sigma is fracture strength and sigma gamma by s is a surface energy and a is a crack length. And I want you guys to tell me now. Hello?
Yes, welcome. Yes, correct.
We just now derived the equation.
C,
Is it C?
C is the
C is the reason for fracture.
Perfect. So, question
Madam, just
8.
ma'am.
can you go back? Can you just
Yes.
show us one? So A goes to other side. Okay, okay, clear. Clear.
The 2 is
Ma'am,
not
one
there.
small doubt, ma'am.
Huh?
Just
Yeah,
a
sure.
small doubt. Actually,
Yes.
I had just since we are right on this topic, I
Huh?
had posted a question in the discussion forum with
Huh?
regards to this surface strain energy and surface energy formula derivation.
Huh?
What I'll do is, ma'am, like I have a 1 minute.
Yes.
Yeah, I have just posted this note which I gave as an attachment.
Yes,
Uh,
sure.
Basically, okay, I'll just read on. So there's a formula which is derived for strain energy, and Sir mentions that UA is equal to the volume of the triangles into sigma square by 2E. So Sir had emphasized the point to remember the form of the equation that he referred to as sigma square by 2E, and then multiplied by the volume of the triangles. So,
Yes.
so it is a central crack. So in the figure, he had shown that there was one triangle above and one triangle below, because
Yes,
of which
perfect.
he takes twice 2 into volume of the triangles,
Correct,
one
correct.
above and one below.
Correct.
And so after 2, then in the bracket we have the triangle area formula, half into base into height. So for which I
Half into
understand
base
that
into height into thickness.
yeah, sorry, because it's a volume. So all
Huh.
3 dimensions. So the base, I understand it is 2A. I mean, the base of the the triangle, the crack, this thing, and
Yes.
the height also. He mentions, Sir mentions lambda into
2A
2A.
lambda. Huh.
Yeah, and lambda, Sir mentions as a proportionality constant, and
Yes, that will depend upon, see, that is a material property. It doesn't
yeah,
have to be pi by 2 all the time. And then it, like when they try to do the derivation, you saw the way Griffith done the derivation, right? And then he was finding out some values. And that was matching that proportionality. They have to give some proportionality constant to something, right? And
right,
they do not know, like they cannot assume that how much that strain energy will be distributed inside the material. That
yeah,
effect will be present throughout the sample, but it will be present maximum at the that tip, that where the crack elongated has happened in the B axis. Sorry, in
right.
the
So
A axis.
Yes, ma'am. So, sir had mentioned that this is a relaxation analogy. So, which we have just learnt it as lambda. Just my doubt is that here the base of the triangle and also the height, both we are assuming it is 2a, is it?
No. Base of the triangle we are assuming it as 2a because that is a crack length.
Right. Okay. Under central
And
crack.
then,
Yeah. Okay.
2a lambda, we are assuming that lambda is a proportionality constant and it also depends upon the material. And
Okay.
that lambda is like here after doing so many experiments, we came to know that it was pi by 2. It was approximately closer to pi by 2.
Okay. Okay.
So
Because
that
the formula is pi a square b sigma square, right? So a square means there is two. I mean, there are two multiplication. There is half into 2a into 2a lambda into thickness. So because that's what. So I think the height also is 2a and base also is 2a. Otherwise, we will not get a square. No, I mean, I hope you got my point.
there is 2a lambda also is there, right? There is also
Yeah.
multiplication factor lambda. So it is not same. Both are not 2a.
Okay. Understood. Oh, okay. Got it. Understood.
If
So
I
lambda.
understand correctly, that multiplication factor lambda is taken with respect to 2a.
Okay. It's a ratio. Okay.
Yes. Yeah,
Right,
they are
right.
everything trying to convert in terms of length of the crack only.
Yeah. Oh, got it. So it is in terms of length of the crack, we are giving that factor as lambda into 2a.
So that it will be
Okay.
easy for us to, further do the mathematical calculation or anything for that matter. That's all.
And just like how you showed, so we arrive at a formula for UA as pi a square into sigma square into thickness by Young's modulus, and for surface energy as 2 into. So about surface energy also, one thing I'd like understood is that since there are two surfaces which are formed, so we consider because by definition surface energy is per unit area of one surface. So here in the crack, since two surfaces are being formed, we calculate as 2 into 2a thickness multiplied by thickness into the gamma s.
Yes, correct.
Because of which we get 4a thickness gamma s. Then sir mentions that he performs, as you said, the slope of that total energy is 0 in that point. So
here, whatever it is coming, I'll tell you only one point here. In the US, first we are considering there is no crack.
Okay. Yeah.
And then now we are creating a crack of length 2a. And to create a crack of length 2a, how much energy is required? That energy, when your crack is formed, it creates two surfaces. That's the reason why we have 2a. And the crack length is around 2a because we are considering inside crack. And then gamma has whatever that is the length of the crack as well as how much ever the surface energy of the material that depends upon varies from material to material. That's why it's gamma s. So for initially we are considering there is no crack and then we are creating a crack of 2a and how much energy is required for that.
Okay. So gamma is also it is gamma is nothing but surface energy per unit area of one surface. So basically
Gamma
you
is
multiply the dimension so as to get the surface energy US.
Yes.
Okay. So then the final one. So then we carry out partial differentiation of UA also and US also. I mean the strain energy also and the surface energy also.
Yes.
So this is where I didn't understand because formula before partial differentiation formula.
Okay, see, I just now wrote the UT, right? Like UT, that total will be UA plus US. But UA strain energy will be negative and then US will be positive. So UA, you have to put it everything in a negative. And you saw in a source graph also, UA was in negative direction and US was in positive and then it was varying linearly. And UT will be UA plus US.
Yeah, okay, understood. So, basically, so when you take the negative, either whichever is negative, so you're saying that strain energy, since it is being consumed, you give a negative notation. So, if we transpose it to the other side of 0, we are actually equating the both. Just that, see, when we see the formula of UA, it is pi a square b sigma square.
Give me one tomorrow, like next week, I'll tell you the exact reason why the strain energy is considered negative. Even I tried to find it, but I thought of like seeing that.
No,
I forgot.
actually, it's not about negative, ma'am. It's just about the how the factor 2 went off. I mean, it's something to do with partial
You tell me where the factor 2 went off. When you differentiate the UA, you get
Yeah.
now when you differentiate UA with respect to A, you will get 2A. A square becomes 2A.
Okay. Oh, yeah. Right.
And then 2A becomes it has power only 1. So differentiation of dA by A, it will be 1.
Okay.
So here the 2 on this side you will be having a 2 pi A. B will be considering it as 1 and sigma square by E. So and then this side we'll be having 4 and then 4 gamma S. So here 4 gamma S was there and then 2 it gets cancelled using basic maths.
Okay. So that A square differentiation becomes 2A. Got it.
Yes. Okay.
Yeah. Thank you.
Hello.
Yeah.
And why the strain energy graph is negative?
Yeah, that's what I said. I forgot to see that part. Like I knew that part. Why it was negative. I forgot actually. Let me just give me next class. I'll tell you the reason exactly. I knew the reason and I forgot actually. I'm sorry.
problem.
Like I
No
thought of seeing that. I'll see that. I'll tell you next week. Okay.
No,
Is it the conservation of energy principle when energy is created? Surface energy is created and then
something like that only. Yes. In order to create an energy, surface energy will be positive. We have to give positive for sure. And let me see. Sir also told the same point. Strain energy
is being destroyed and same way surface energy is being created.
something like that. Yeah.
in order to create a crack, surface energy is required. That's why Sir told it is positive, but strain energy, I don't know what is the case there.
Let me see whether it is actually the conservation of energy only or anything else reason is there. I'll tell you by next week. Okay. Okay.
Madam,
So-
this fracture strength. Okay, you are using sigma and there is sigma root A. Actually, when these two are used, actually, just can you please differentiate? Okay, formula wise, what is sigma root A?
Sigma
Root A.
root A.
Yes.
Actually, this will come later on. Now you don't worry regarding this. This is especially we do it like this because so that this is considered as like fracture toughness also you'll be finding out. And this one will become constant. This is a constant actually. This is constant and this is surface energy is a material property. Elastic, this one is a material property and pi is constant. So everything becomes constant for material. And then that constant is called something actually that also will come. There is a reason why they write it in sigma root A. Fracture toughness, this entirely something called fracture toughness or something like further. It will be present in next class. I'll also have to read about it a little bit more. So,
sigma is fracture strength. Sigma is fracture strength and sigma root A is fracture toughness. Shall I take it that way for time being?
No. Don't take it for any being. Like I'll see properly and then I'll teach you properly in the next class only. Don't. For now, you just yes.
Maybe it is related to some stress intensity factor or something like that.
K, that one only. But I forgot if this is K or something like that will come again in the next class. We will discuss more detail in that one in next class. It's better to leave it there rather than me telling something wrong to you guys.
Yeah. Sigma, I think just to add to Suresh, I think sigma is the normal stress acting on that specimen in consideration.
Okay. In the
shear stress and normal stress.
Actually, it was asked what it is a fracture strength. When it was asked to
sigma F is a fracture strength.
A fracture strength will be to that A, that root A comes to the right side. That's all, is it?
Yes, that's all. I have discussed just now, right? This is a fracture strength. No, this is a fracture strength.
Simultaneously, you are discussing about both. That's why just I want to know the difference.
No, this is fracture strength. Don't get confused. There is a reason why they always keep it root A to this side. But for now, this is a fracture strength. You don't get confused with anything. This is a fracture strength.
Madam, the theoretical strength also just can you formula? Just can you please
Theoretical strength of the material.
Formula.
It is given in the group sir's lectures, right?
It
Yeah,
is,
it is given
yes.
under root
Sigma
n
TH. Yeah.
sigma
Let me see.
sigma rho s by b. Is it that?
It's, I think, square root of Young's modulus multiplied by surface energy divided by B. And that is interatomic distance, no?
Distance.
Separation. Yeah.
Yes.
Square root of Young's modulus into gamma s by B.
Okay, madam. Here also we need not to consider because it is it was told that it is a thin plate. That
I don't think so. B
Seven
is B here is interatomic distance, not the thickness of the material.
correct, madam. Here also the theoretical strength, does it depend on either plane stress condition or plane strain condition?
Okay, theoretical strength will only depend upon interatomic distance. When two atoms are present, how much when you try to pull them, how much is the strength when there is no defects present at all in the material?
Okay, it is nothing to do with plane stress condition or plane strain condition, is it?
See, one thing sir was telling, like, this is an ideal case. It is very difficult to get an ideal case for you, right? Like, that's the reason. So one point I wanted to discuss is for sure, like, when we have a bigger sample, the chances of that having the surface cracks or voids inside the material, for that matter, will be higher. So for instance, you consider we take a very small sample here where there is a negligible, like we are taking in such a way that there is no flaws present in the material and atoms are nicely arranged one above the other the way it was supposed to be arranged. Okay. Then you do the tensile strength of the material and then find out that how much it is present. That will be like it will be having higher compared to that of the bulk when you take it in the bigger one, because the chances of finding flaws, that whether it can be surface crack or the internal crack, internal defects will be higher. So that's consider when whole material is ideal, when there is no cracks or voids or nothing is present, no defects are present, then you do the tensile strength. What is a strength you get is a theoretical strength. Because
Yes,
if you already have cracks present, then it will be acting as a stress concentration region and then it will not be uniform, blah, 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 and all these things which we are studying now.
There is nothing like that plane stress or plane strain in this condition, because theoretically
No,
this is
no.
the ideal condition. It is in all cases it is same.
It should be ideally same.
Okay.
Plane stress or plane strain. Let me remember, like plane stress with thickness. Let me get this question also. Like before, instead of me telling wrong, I'll just note down the question.
Because in the present assignments and all based on these actually.
Theoretical. No, it is just between the atoms. No, it is not. Theoretical strength will depend upon thickness. Who is joining now? Okay. Anyway, so we'll go to next question now. The strength of glass wire increases when the diameter of the wire is decreased. Flaws within the dimension, flaws of the wire diminishes when the diameter of the wire is reduced. Is both like what just now we discussed this point, and I want you guys to give the answer. Both the statement are true, and statement one is not the reason for statement one. Both the statement are true. Statement one is the reason for statement one. Statement one is true and statement two is not true, and both the statements are false.
B, both are true, and 2 is the reason for 1.
So you're telling that the strength of the glass wire increases when the diameter of the wire is decreased.
Yes, yes.
And then flaws within the wire diminishes when the diameter of the glass wire is reduced. So if you reduce the wire dimensions, so the flaws gets automatically reduced. Flaws within the wire diminishes when the diameter of the glass wire is reduced. That is correct. Both are correct. Yes. And how is reason 2 is statement 2 is correct for statement 1? Reason for statement 1?
Size effect.
Yes, so yeah.
Then there is a possibility of more flaws. Manufacturing.
Just the strength of the glass wire increases when the diameter of the wire is decreased. That is perfect. And I'm asking that how is reason statement, this statement 2 is a reason for statement 1. How? I'm just asking the relation between these two. Flaws within the wire diminishes when the diameter of the glass wire is reduced. Yes, flaws also reduces when we go to the smaller wire diameter, where like nearly we can go to approach to the critical strength. I'm just asking how is this both related? How is
You're okay. I get it. So actually the diameter has to be constant. Length when reduced. Sorry, thickness. No, wait.
No.
I think I'm getting wrong.
Ma'am, may I try? Actually,
yes,
the
sure.
imperfections will get reduced when the diameter is reduced. This is what you
Can
have
you tell it
explained.
loudly?
The imperfections will get reduced
Huh?
when diameter is reduced. This is what you explained for a few minutes.
Yes.
And because of this, the strength may get increased because there is no imperfection, so there is no the onset of crack will get delayed.
Sir had
Maybe-
mentioned glass being a brittle material, the cracks will heal.
Cracks will heal.
Yeah, when the stress is removed.
No,
For a
actually,
glass.
both the statements are correct, but statement 2 is not the reason for statement 1. How can by flaws within the wire diminishes when the diameter of the glass is reduced? Correct, that is fine, but not just because of the flaws, the strength of the material increases, right? Because like, yeah, that is not happening, but this is not the reason for statement 1.
When flaws are reduced, the fracture strength approaches the theoretical strength of glass.
Yes.
So can we not say that if
Then
the
definitely the strength of the glassware increases, madam.
yeah, since the flaws diminishes.
That is actually correct. It's a valid point. Even question 8, let me see it again. Then
The number of flaws means the size effect also it will influence
there.
There is a size effect means there is a relation between the endurance limit and the size effect. And then
Yes, that is there. Like, but statement 2 is not the reason for statement 1. And anyway, I'll see this, and I wanted to discuss one more thing. You guys have heard about nano materials?
Yes, even nanomaterial also same logic applies.
Exactly, same logic applies. Actually, that's true. So even along with that, the defects, not only the defects are very less, the surface energy of that material will be very high. So like that's why it will be easy to make composites and all. That is one thing. And when you see that strength of that material, right, it will be very high, very, very high. That's why nanotubes are like now in like nanotubes or nano rods or like nanostructures. All these things are emerging more and more nowadays because of this. So yeah, I'll check this again. We'll go further for now. Like we have so many things to cover. Stress corrosion cracking occurs due to the action of what? Like I have already explained this stress corrosion cracking in the last class. So sustained static stresses, corrosive environment, high temperature, cyclic stresses.
A and B.
A and B. Anyone has to say anything else? English solution possesses a mathematical difficulty in the limit of perfectly sharp track. select suitable options in this in support for the above statement in the context of an infinite plate with an elliptical hole. So we know English that he did not consider the surface energies, the formation, and he told that whenever there is a small amount of crack that is present, that at the crack tip, because it will be, the stresses will be very high, and then it will, the whole sample will be shattering and it will not be able to take, and then it becomes like it is going to say that cracks will be propagating in every way and then whole material gets shattered, but that is not what actually happened. And according to his English solution, it had few difficulties. So what are the suitable options below this? You have to choose. When the value of the semi major axis 10 to 0, that one B 10 to 0, the stress concentration factor becomes infinite. New approach of mechanics to understand the real behavior of material is needed. The solution suggests that when even for small load, the crack may grow and break the material into pieces. Fracture strength of the material is less than the theoretical strength.
All options looks to be right.
This is
Is
right.
Except B.
A
Except
A. Is it semi-major axis or by 2 or B tends to 0, right? Not B
yeah,
by 2.
correct,
So
correct.
this is not wrong, right? So I want you guys to solve the problems. That's the reason why I'm rushing, because these are more important than theoretical questions. So shear stress in the material at a point is given 50 MPa, and the strain energy density of the material having a shear modulus G is 80 GPa due to shear stress. Then we have to find out the strain energy in the material. Can you guys solve it and then tell me how it is done? I'm giving 1 minute for this. This is not that difficult. First, tell me how is the way that you guys approach? Can someone volunteer and tell? No one is there?
Since the stress acting is a shear stress
Okay.
and shear modulus, so we can consider shear strain is going to happen. It will be a shear strain energy.
Okay, fine. Shear strain energy, fine.
So there is a formula: shear strain is equal to tau xy by shear modulus. I'm just going back to my notes.
Yes. This one you're telling? In any direction?
Yes, yes.
Are you
Yes,
sure this
yes.
is the correct equation? Who will tell that is this the correct equation to use for this question? Okay, I really want you guys to reply. Or else take down this question and we will discuss this question in the next class. And I want you guys to tell how you guys approached also this question, by the way. Here, just can see this strain energy density. Okay. Anyway, we will not discuss. I'd not give the answer for that. Though I have solved that, we'll be discussing that again. I hope you guys have noted the question. You can take the screenshot or anything.
Ma'am, one query here.
Yes.
Can you tell me the unit of strain energy density?
Try to find out what is strain energy density first then.
Okay, ma'am. Thank you.
Anyway, in the question itself, you have clue also. You want me to solve here only? You guys will solve or will solve?
Please solve.
Okay, I thought of going for next. Anyway, so here is when they ask strain energy density, it is when considering that shear stress is happening and then load versus elongation or whatever it is. Whatever the strain energy that is stored within this material is then strain energy. Here it is not, they did not ask for just strain. Whatever here is there is just strain. That's all. Strain because of shear stress. That strain is it is happening in either in XY direction or any direction for that matter, just because of the stress that is applied, shear stress that is applied. But what they are asking is strain energy. So the formula for strain energy, as we know, the area under the curve sigma xy all square by g. You got it now. This is the equation that you have to use to solve, because they're asking the strain energy, because that strain energy density that is happening because of shear stress. And we know that in the strain energy stored will be the area under the curve. So when we apply the load in shear, this in shear, and then elongation will be having the gradient anyway.
Madam, this is not the whatever you have written initially. That is not the correct one. That is only strain, is it?
Strain energy we have to.
That is sigma xy is equal to tau xy by g. Here
Square,
sigma xy.
tau square energy is equal to half tau square by g. We will solve. Can at least you guys solve and give me the answer now at least.
What is the strain energy? This notation for this strain energy density.
It's given, right? Kilojoules per meter cube. You try to solve this and then convert all the units that you guys have. You will reach here.
No, madam, not units. Not that notation like sigma, tau.
Strain energy. I'm guessing you only. Strain energy. So now at least you guys solve it and tell me. And please see that this is MPa and this is GPa.
In kilojoule per meter cube.
And then convert Pascal.
Okay.
No,
I did took Newton per meter square.
And Newton again is?
Force, stress into area. Okay, joule per meter. I got a value 15625. Just trying to 5625.00.
15.6.
No. 15625 decimal 00.
This is the answer I'm giving. You might have missed. This is the answer.
No. Yeah, so in joules it may
anyway,
be.
It is there, right?
Right, yeah.
And now, so don't get confused. The only point I wanted to discuss here is don't get confused with the strain to strain energy. You have to make sure that this is just a strain and not the strain energy. Someone told me in the beginning that we have to use this formula. So that is what I wanted to clarify here. That's all. Okay. You have to find strain energy, not the strain. So select the expression for the strain energy stored in the member when stresses are acting along the three Cartesian coordinates. Come on, guys. First, so that we'll go soon. At least it's already 8:06.
It's option D, going by the notes.
And yeah, we're going by the notes. It's option D, and the similar way, even option A is also considered to be right actually. Both the options are right. So you can just take a note of this. Both the options are actually right. So with the reference, I've already discussed this one. So I want you guys to give answer quickly now. With the reference to the graph for the plate with a central crack under a fixed grip, answer the following questions. The crack growth in the zone A will be zone A. This is zone A below the slope 0. Come on, guys, fast.
It is
Is the
catastrophic.
huh?
Incremental.
Correct.
Like,
Who said catastrophic? I'm serious. I want to know who said catastrophic.
yeah, myself, Suresh. Because that
Hi,
is a critical
Suresh.
crack. It is a critical
In the
crack.
zone A, in this zone.
Acha, okay. Sorry, I thought it is at the peak point, the point where it is shown. Okay, clear. It is incremental.
The crack growth in the zone B will be
Catastrophic.
perfect. So this one you guys should be able to answer. Find the fracture strength in MPa of the glass fiber with a crack length 4 mm. If the surface energy of the glass is taken to be 0.54 Newton per meter and Young's modulus is 62 GPa. So please solve this and then give me the answer. I'm sorry. We still have few more questions left, so I'll give only 1 minute to give this question. Give me the answer. It's all there. You have to just distribute and then give me the answer. First, tell me which formula you guys will be using, by the way.
Root of 2 by pi into Young's modulus into surface energy divided by A, crack length.
Yeah, perfect.
It is around 2.3 megapascal.
Perfect. Everyone got the answer?
Here we have to consider this crack length into meters, is it? We have to convert it into meters.
Yes.
We'll go to next. And we have few more questions left. I'm sorry. I haven't given the answer. I'm really sorry. Like I know the answers. Like anyway, I have given the answers wrong here. Like I'll edit it in next PPT. This one is not. Are you guys able to see the next? So no, nothing is there in mine. It was saying wrong. Okay. Anyway, this is a load displacement graph shown in the experiment conducted on double cantilever beam specimen for a constant load, and we know how the constant load happened. This constant load applied is around 150 Newton, and the crack grows from A to A plus DA. The initial displacement is 16, and the final displacement corresponding to A plus DA is 24. Using the data provided, answer the following. The change in strain energy in Newton millimeter. So this you guys know. When the crack is, should I explain this one, or like you guys know are well aware about the concept, the constant?
Please explain.
I'll explain. Okay, fine. This is a constant load which we are happening. So when crack is present, when we are having the crack length of A, and we are applying the load only in one place, and then this is kept constant. This is a crack length A, and when we are doing load displacement curve, we are getting one line, that is we are still in a linear region, and we are also doing, when we increase the crack length TA, and what do you think the stiffness of the material, that overall resilience of the material, we know that it will be reduced, right? For a given load, for any given load, it will be having some amount of A. This A will be smaller compared to this displacement happening. This one will be having little bit higher. So if initially itself the crack is higher, like if initially itself consider it is 10 mm and this was 20 mm, we are like doing a little bit higher still. If initially itself the crack is higher, then the stiffness of the material or the resilience of the material or the it will be lower compared to that of the because initially itself the crack is already present. So the energy ability of the material to store that any energy will be lower compared to that of the crack, which will be having smaller in length, right? So that's the reason why A has more strain energy stored compared to A plus dA, which was already present in the initial crack. So now we will see at particular load, if you apply any particular load, for instance, now sir is giving 150 Newton, then what will be the energy that is stored inside the material, inside that crack with having A and crack with having A plus dA. And when we see that, how do we do the energy one? Like we will be calculating how much to calculate. Like we know the area under the curve, it is already given. We don't have to go the stress applied and then small it is and all. So half of 150 into 16. So area under the curve is and area under the curve for crack with having A length. And then if you see the similar way, the area under this curve will be the strain energy stored in this material, right? That's perfect, right? Until now, you guys are with me, by the way?
Yes, yes.
Yes, ma'am.
So you have to calculate how the change in strain energy. So in order to calculate the strain, you tell me how to calculate the strain, change in strain energy, like how much it is present in this material and how much is present in this material. And if you subtract these two, you will get the change in strain energy, right? And as the load is constant here, the displacement will be varying. So we have an equation for that, or also we can calculate using this. First, we can calculate the area under this curve and calculate area under this curve and then subtract, and then we will be having the change in strain energy. Can you guys tell me now what is the answer for that?
0.6.
In Newton meter.
600.
And this is mm. Sorry, Newton mm. Sorry. Who said 600?
It is 600 Newton mm.
It's a good number.
Yeah, you guys calculate first. See 24 into 150, 16 into 150, and subtract and tell me. Sorry, of course you'll be having 24 into 150 minus 1/2 into 16 into 150.
That we have to convert into meter, no? That.
No, it is not required. It is Newton mm only, so no need to convert it.
Got it. Okay, I convert into meters. Okay.
So everyone got 600 answer as an answer? Did everyone get or not? Can we move to next question?
Madam, it is 600 is the answer. What is the significance for the shaded portion that you have shaded with one side yellow and other side blue? Actually, what is the significance of this shading these areas with different color? Actually,
See,
what they are
this
indicating?
yellow inside this in this region will be the strain energy stored for A at this load, and this blue region is the strain energy stored for A plus A in this region. This complete. This is a common one for both of the material, and then this is pink. Like it's if you add yellow plus pink, we will get the extra work done that we how much external work has been done by at the same for A when we are going from A to A plus delta A.
No, madam, just please repeat this blue and white together. It is giving the strain
Blue
energy.
and pink.
Oh, blue and white.
No, yellow and pink.
Sorry, yeah, yellow and pink. I'm sorry, yeah, yellow and pink.
What did you indicate, madam? Yellow plus pink is
external work done. Like you remember sir was telling this is the amount of extra work that we have to do to get to this one. Like if we had a plus delta A for the particular and we had one more material with a crack length, and then how much for that particular load only, how much extra work has to be done so that you go to a plus delta A. From A to A plus delta A.
I'm sorry to interrupt. Actually, if I'm not wrong, that external work done is the area of the rectangle, which is
This rectangle.
yeah, the area of the rectangle, which is 150. I mean, it will be 150 multiplied by dv.
24 and 16.
Yeah,
This
yeah.
one, this one. Half
Yes,
into.
ma'am.
So
No.
that one will be 24 minus 16.
16 multiplied by 150. The
No,
load.
no. This delta V.
Yes, for the external work done.
Yes. We have a question with external work done also. This is a question with external work done. So 150 is this one, and then 24 minus 16 will be delta V into half of that. That is a formula, right? I'm trying to find the formula actually.
No, it's just the area of the rectangle, I think, for the work done. I remember in the first class I had the rectangle as in, so you have a length of the rectangle is 150 Newton, which is on the y-axis length. And the width of the rectangle is 24 minus 16, which is 8.
Correct.
So where
24 minus 16.
1 by 2 is not applicable, no, madam?
Yeah. 1 by 2 won't be there, I think.
Area of the rectangle, this rectangle, right?
No, rectangle, ma'am. Yeah. The blue and the blue portion and that pink portion combined together.
Acha, no, can the strain energy. Acha, this is strain energy. Work done is extra. It was this much, but then see, this much was the present work. So this much was.
So
the work done.
sir had mentioned in the under constant loading, sir explained that the strain energy increases.
Strain energy increases, correct.
So because of which it is the difference of the area of the two triangles. That is, first one will be half into 150 into 16.
So if it is the difference in the area of the two triangles, then it will be this triangle then. No. The yellow plus pink. Yellow, yeah, that's what I said actually initially. Yellow plus pink is a
change in strain energy.
Yes, change in strain energy.
Yeah.
No, madam, pink is not pink. Sorry, pink is not neither it is there in that second case or first case. In the first case, it is only 16 into 150. In the second case, it is 24 into 150.
But in order to do the external work done, it has to be, this is the external, this is initially it was present until here, and later on it was present until here. You have to see this is amount of like when dA approaches to 0, you remember, like, and then this actually goes to and then merges with this curve. There was a point where sir you was telling. You remember that? And this is the this is the region that will be varying actually, with varying the crack length.
Sir mentions that there is a load of P which is attached by means of cable and it is attached to that material. So when the load also moves down by delta V, that is the external work done.
Also, yeah. When we,
load has moved,
something
load
like
has moved from 16 to 24. It has moved here.
No. Load has not moved from 16 to 24. Load is constant, 150.
Sorry. Load is 150. The displacement has taken place.
Yes, displacement has taken place. So here it will be here. And then if crack length is A. And then if crack length is A plus delta A, that load will be moved a little bit more.
It will be delta V only, just like how much that incremental length the
Has
crack has
happened.
increased. The same thing, the load will come down. That much.
So that will be the area of this triangle. That area of this triangle is half of the load applied at what load we are doing into the displacement, the delta V, del V. Newton millimeter. Then only Newton millimeter also will come. Okay, let me
No,
see
because
this question.
the load is constant. Because the load is 150 is not changing. It is constant. And
Yes.
initially this load was at when the crack length was 16. Then from there it moved to a incremental value of 24.
Yes.
That's why I think it's
Okay, anyway,
area
this
of
question
fracture.
17 again I'll see. We will discuss this question 17 again in the next class. But if I'm not wrong, this is the area of this triangle is the external work done that we sir even mentioned very specifically regarding this, and then he showed that this is the external work done. So I'll anyway see that, and then if I don't get it, I'll talk with sir and then discuss this again once more.
Yeah, external work is given that P1 into dV, whatever P load is there into dV, that's 16 minus 24. This is only that rectangle that is blue plus pink. That's
So
what
this
we
one.
Yes, yes,
Okay,
yes,
madam.
Okay.
yeah.
Anyway, we will see that again. Like we will discuss this part again in the next
Sure.
class. So,
So
in
if
this
we
experiment,
do
this is the last question. Yes.
no, the 1200 value you get it when you multiply 150 into 8.
Yes.
150 into
Yeah.
8 gives you 1200.
Even I did the same, but then I might have got confused with the concept, I guess.
Yes,
Maybe.
yes.
Okay.
That pink
Anyway,
and blue gives the work.
pink and blue is the external work done. Yeah, it is. The only reason why I'm getting confused, this much is the initial, and this much is the later on, and this much should be the external. That like only that much should be the external work done. To be frank, so that's where I'm getting confused. Like I'll see this part again anyway.
Okay.
So in the experiment, the stiffness of the specimen due to the crack growth. So it will be enter I if it increases, enter D if it decreases.
It decreases.
Yes,
Decreases.
perfect. Sure. That's it. Thanks, everyone.
Madam, just you can.
Thank you.
Record
Yeah.
few things. The recording can be stopped.
Yeah, we can stop the recording.